Hey guys, my name's Ian Woods. Today I'm teaching lesson plan 1 to Matt Southard. He's the other CFI I'm working with today. So today we're going to go into principles of flight. Like I said, it's lesson plan 1, so we're going to get started here. All right, Matt, have you ever built a house before?
Yes.
What is the first thing that you do when you build a house? What is the most important part of any structure?
You gotta start with the foundation.
Foundation. Foundation is critical in the development of that house, that structure. Today we're going to build a foundation for aviation. Today we're going to start lesson 1 of the introduction into the aviation world and the community. This is going to start getting you thinking like a pilot and start getting you thinking about aerodynamics, basic principles of flight. That's really going to help you out. Also, this is going to give you a level of understanding of what we're going to expect from you to understand as we continue out through the rest of the semester and understanding what's important and what's not. It's also going to give you good study habits. It's also going to give you a good understanding of how how to learn. Okay, this is going to be the hardest you've worked in your entire life. This is going to be the most fun you've ever had. You're going to have buddies who are in different career fields that are doing things that aren't enjoyable to them, but this is going to be a blast. You're going to love it. But it all starts today. It all starts with this foundation. It all starts with this basic understanding of what we need to understand. Okay, so brief overview of the lesson we're going to go over today. We're going to go over structure of the atmosphere. We're going to go over atmospheric pressures, basic principles of lift, and then a little bit into wingtip vortices. These are all important to understanding because it's all going to correlate with future lessons in aerodynamics, drag, and maneuvering. So to understand those future topics, we really need to have a strong foundation and base of this basic stuff. All right, so when you think of the atmosphere, what do you think? What do you think of?
Air.
Yeah, that's what everyone thinks of. They think of the atmosphere as air particles floating around, and I'm just a part of it. That's not how we need to think of it now. It's okay that you thought of that in the past. I'm not saying what you thought of is wrong, but to visualize aviation and understand it properly, you need to visualize air as a fluid. I know that's a little weird, all right? To understand air, you're really going to have to understand fluids because there's fluid properties that air has that's really going to correlate well and translate into aviation, okay? First one's going to be viscosity. Viscosity is how the stickiness or how the runniness of a material. You ever played with maple syrup before? You ever had pancakes?
Yeah.
Yeah. What happens when you pour that maple syrup on that pancake?
It oozes.
It oozes. It spreads. Now, if I poured water on that pancake, what would be the difference between the two?
Water's a lot thinner.
Water's a lot thinner, right? It's got a lower viscosity. Maple syrup has a higher viscosity, meaning that it runs slower, it sticks together, and it wants to stick together. Viscosity basically is a property of fluid that causes it to resist flowing. Okay, if I take a metal sheet, I pour maple syrup down it, it's going to take a lot longer than if I poured water down it, right? You see that? Viscosity means air particles want to stick together more. They don't want to separate. They don't want to move. Okay, that's viscosity. Friction. You taking a physics class, I'm assuming? Sweet. When you guys study friction, what did you guys think of? What did you guys study?
Basically, the movement of an object on top of another object.
Resistance. Resistance is the key word when it comes to friction, okay? So if you're going to remember anything about friction, I want you to remember that friction is the resistance that one surface or object encounters when moving against another. So this desk right here, I was going to pull it. That carpet is going to put a certain amount of friction that I need to overcome before the table is going to move, okay? Why is friction important in aviation? Drag. Drag is something we're going to talk about. You're going to be talking about drag in private grounds, instrument ground, and commercial ground. Drag's always going to be there. It's always important because it's very important for you to understand and visualize flying when you can see drag and its important factors. All right, cool. Last thing I want to really talk about with the atmosphere structure of it is pressure. All right, pressure is a force felt perpendicular to the applied force. Okay, so pressure is a force applied in a perpendicular direct to the surface of an object. If there's anything you remember about pressure, I want you to remember that pressure moves from high to low. Okay, so let's draw something out real quick. If I have, let's just say it's a block of wood, right here. All right, you see my block of wood? Now I have 10 newtons of force. Newtons is the value we would give the force going this way, and I have 9 newtons of force going this way. Here's lower pressure, here's higher pressure. Which way is that block of wood going to go?
It's going to fall to the left.
It's going to go from high to low. That is the most important thing I want you to remember. If you get anything out of this lesson, if you get anything out of this we just talked about, pressure moves from high to low, always. 10 newtons is going to overcome 9 newtons. It's just basic math, okay? So it's simple like that, okay? Remember that. High to low. Cool. So that is basically the structure of the atmosphere, if you will. That's kind of the basic principles for that. Now we're going to talk about atmospheric pressure. Why is atmospheric pressure important to aviation? Atmospheric pressure is directly related to performance of the aircraft, to the weather, and so performance, weather, and it helps lift an aircraft. Okay, so atmospheric pressure is extremely important to aviation. You can see now we want to understand it. Okay, we're going to break atmospheric pressure down into two parts: density altitude and pressure altitude. Okay, pressure altitude is going to come first. Density altitude is going to come second. We're going to calculate both of these basically to calculate and understand our performance, if you will. So we're building a pyramid. That's really what we're doing. Atmospheric pressure is, we'll call atmospheric pressure the entire pyramid, and then, but we're going to break it into 3 sections. First section down here is going to be pressure altitude, PA we'll call it, the P. Second is going to be density altitude, and this top one right here is going to be performance. Alright, there's performance. So, to understand performance, we have to be able to calculate density altitude and understand it. To calculate density altitude and understand it, we have to calculate and understand pressure altitude. So it's a building block. We're building up, okay? Like I said, we're building a house, foundation, structure, and then drywall. Let's go with that for basic understanding. One thing with atmospheric pressure, there's a standard for it, okay? They went out and they drew they figured out what would be a standard day, what would be a standard atmospheric pressure, and they came up with this 299er2. 299er2. Some of you are going to hear a lot in your classes. It's very important to understand, but that is the standard atmospheric pressure at sea level, okay? So some days, you're going to have days when it's like, it's a non-standard day. So you're going to have days here at Lynchburg where it's 3092. What does that mean? Why is it weird, and why do we need to understand it if we're having a non-standard day? Can we just not go flying? Can we only go flying on this? I really hope not, because I've only flown a couple times when it's 299er2. So what do you think? You think it's important to understand this?
Yeah.
Yeah, because it directly relates to our pressure altitude, which we're going to get into. Pressure altitude is the height above the standard data plane, which is theoretical level where the weight of the atmosphere is 299er2. Basically, bring it back in a nutshell, the difference between the two. That's what pressure altitude. That's what we want to understand. There's a formula we're going to go through that I want you to write down so you can understand how to calculate pressure altitude. Okay, pressure altitude is equal to, let's put brackets and then a parentheses, 299er2 minus 3099er2. Okay, times 1,000. The standard lapse rate, the standard rate of change, if you will, for atmospheric pressure is going to change 1 inch of mercury per 1,000 feet. 1,000 feet. That's where we get the 1,000 from. Okay. And then you're going. Oh, yeah. And then we're going to add it to our field elevation. What's the field elevation here at Lynchburg?
938.
Yep, 938. So we're going to fill in the blanks here. 938. Go backwards. 1,000. Now, what is 299er2 minus 3099er2?
Minus 1.
Exactly. Give me a negative 1. So we're going to just put a negative 1 right here. So negative 1 times 1,000.
Negative 1,000.
Yep. Negative 1,000. Very good. And then plus 938. My answer is going to come up to what? Negative
62.
Correct. All right. So now I understand my pressure altitude.
I do have a question.
Go ahead.
The 30.92, will it always be 30.92?
No, it will change. You're going to get that from a local altimeter setting or an ATIS or a METAR. So when we go in basic flight, when you're going to go for your first flight, you're going to pull up what we call a METAR, or you're going to also listen to the ATIS. It's going to give you a local altimeter setting. That local altimeter setting is this right here at sea level. So it's going to be the altimeter setting at Lynchburg if Lynchburg was at sea level. So that's exactly what this is. So a good question. It will change. It's going to be different on different days. It's going to be based on the weather, okay? So, you can have a general idea when you come in, but when you look it up, then you're really going to start understanding what the atmosphere is like and the pressure altitude is going to be like. So great question, okay? All right, so that's pressure altitude. Now we're going to talk about density altitude. Why do you think density is important? Exactly. It's cool. I got to talk about it. So let's say we have 2 boxes, all right? Are you familiar with how engines work at all?
Yes.
Cool. So engines, it requires fuel, spark, and air, right? if you have more of one, like you say you have more fuel or more air, is it going to be, you're going to have better performance, more power?
No.
If you put more air in it, are you going to have more power?
It needs to be the proper
It
mixture.
needs a proper mixture. But let's say we take out a little bit of air. So like we're having a normal amount of fuel going in, normal spark, but we take out a little bit of air. What's going to happen?
It's going to be worse performance.
Exactly. Performance is going to go down. So as long as it's balanced, it's good. But we start losing that density, we start losing those molecules of air, it's going to be worse, right? Makes sense? So we have two pockets of, let's say, cubes of air here. Let's say we have, what's that, eight molecules of air per that cube, and we have 6. So here we have differences in density, okay? Here we have density 1 and density 2. Density 1, as you can see, has more molecules of air in it, right? So you say that's higher density. So high density right here. Cool. So where would we find that in the atmosphere? Would we find that up high or down low? I want you to think of the atmosphere. So here's the ground right here. And here's a tube of air. Here's little Matt Southard standing right down here. Sorry, your legs are doing a little weird thing. Think about this like when you're diving. Have you ever gone diving before?
Mm-hmm.
So when you go diving, what happens when you go lower? What happens to your ears?
They hurt.
They hurt. Pressure is getting to you. The pressure is getting a little too hard for your ears and what you're used to. So the same concept, like in a liquid, works in air. We have molecules of air all throughout the atmosphere, but molecules like us are subject to come to gravity. They get compressed when they get pulled down. So there's going to be more molecules of air down here with you, Matt Southard, but less up here, higher in the atmosphere. Okay, does that make sense?
Mm-hmm.
So bring it back over here. If we have a higher density, is that going to be in a higher altitude or a lower altitude?
Lower.
Exactly. So a high density actually equates to a low density altitude, right? So let's flip it. If I have a low density, where is that going to equate to on this chart?
High.
High density altitude. Awesome. That can be confusing because people often think of high density altitude. No, high density equates to a low density altitude, okay? So we've talked about how it can affect performance of the aircraft because based on the engine, how the engine works, right? So if we have less air with the same amount of fuel, it's not going to work as efficiently. We're not going to produce as much thrust. So we want higher density. We want our plane to act like it's flying at a higher density. So when we calculate density altitude, what we're actually calculating is what our airplane feels like it's flying in. So we take away all our altimeters. We take away everything we know. And we based our aircraft solely on how the plane was performing. Density altitude and how our plane's performing and what the altitude it's flying at will be equal. Because our plane is going to perform like it's at a certain level, even if it's at a different altitude. That's density altitude. That's why it's important because it's directly related to the performance of the aircraft, the lifting capabilities of the aircraft, and the thrust produced by the propeller. So yeah. Cool. So let's go, I'm going to give you another equation. So here's equation 1. And that goes right here. Okay? So now we're going to talk about density altitude. We're going to get another equation for that, okay? Density altitude, we're actually going to take pressure altitude. So our pressure altitude plus 120, and then it's outside air temperature minus a standard temperature for the day. So standard lapse rate for temperature, because we have standard lapse rate for temperature and atmospheric pressure. Standard lapse rate for temperature is going to be 2 degrees Celsius per 1,000 feet. So altitude, like you said before, is 938. Let's call it 1,000. All right. So standard day is 15 degrees Celsius. So if we go up, all right, what is that going to do to our temperature?
13 degrees.
13 degrees Celsius is going to be our standard day. So minus 13. Cool. Very cool. And make sure that's it. 120. Yep. Cool. So let's say today is 14. Let's say it's 15 degrees Celsius here. All right. So go ahead and pull out your phone and get ready to do some calculations for me. Density altitude is equal to negative 62 plus 120. And let's say it's 15 minus 13. Okay, so 15 it's gonna be hotter than a normal day, hotter than standard. So 120 times 2 is what?
240.
240. Here's 240. Pull up, and then negative 62 plus 240 is
178.
178. All right. So our density altitude is equal to 178 feet. But our pressure altitude was negative 62. Why did it change? Non-standard temperature. Density altitude is simply stated pressure altitude corrected for non-standard temperature. Temperature has a huge effect on the performance of the aircraft because it has a huge effect on the density of the aircraft it's flying at. So my plane, instead of flying at negative 62, which would have been better for performance, like we said, because we'll have higher density, better performance of the aircraft, is now flying at 178 feet, which is still good performance because we're lower than what we're here at Lynchburg, but it's not as good as if it was there. You understand? Any questions? Awesome. So that is why atmospheric pressure is important. That's why we study it. That's when we go through it, because basic calculations and understanding performance start here. All about aviation is understanding your airplane before you even get into it. You got to stay ahead of the ball. You got to stay ahead of the aircraft, because the instant you start falling behind, you start playing catch up, you start missing things, you start making mistakes. Being ahead of the aircraft starts with these simple calculations here and here. Density altitude here, and then we can understand our performance. All right? That's when we study it. That's why it's important to understand it. That's why it's important for you to get this and be able to do this before each flight. Okay? Any questions before I erase this? All right, cool. We're going to now break it up, and we're going to go talk about the production of lift. Why is lift important in aviation? Would we get off the runway without lift?
Nope.
Yeah. It's kind of important. All of us would be out of job if we didn't have lift, right? So to break it down, I want to talk about three things: Newton's laws of motion, Magnus effect, and Bernoulli's principle, okay? So we're going to first talk about Newton's basic laws of motion. States that, first law says, every object persists in a state of rest or uniform motion in a straight line unless it is compelled to change that state by a force impressed on it. All right, so I have a ball. Is that ball going to move if nothing touches it?
Nope.
So I put a little force on it, it's going to move, right?
Mm-hmm.
There's Newton's law 1, okay? Now we're going to jump down to law 3. For every action, there's an equal and opposite reaction, okay? So I want you to think of this in terms of propeller. So let's draw a little propeller here. Which way is that propeller shooting the air, pulling the air back? Or I guess I just answered your question. It's coming back, right? So the P-hat gives a great example of it. The P-hat actually says right here, the propeller pushes back the air and consequently pushes the aircraft forward, equal and opposite reaction. So the reaction of pushing the air this way actually pulls the plane in that direction, equal and opposite reaction. There's also a part of that downwash. We're going to talk about that once we get some airfoils and explaining that. That also comes into play in producing lift, okay? Now we're going to talk about Magnus effect. So here we're going to say this is Newton's law, so we'll go NL. Here's 1 and 3, all right? And then we're going to go to Magnus effect. To understand Magnus effect, you really need to understand the Coanda effect. Let's take a golf ball, all right? 2 golf balls, 2 scenarios. We have a stream of water coming this way. When that water hits the golf ball, is it going to just bounce off of it and deflect? Or is it going to kind of hug the surfaces and drip off kind of almost below it? Option 1 or option 2?
Option 2.
Option 2. This is the Coanda effect. Why is that important to aviation? I'm going to get into that in a minute, okay? We're going to break that down. But to understand Magnus effect, we need to understand Coanda effect, okay? Because let's take this golf ball again. You ever played golf before? If you're anything like me, I slice the daylights of every golf ball I hit. I don't know why, I'm always looking for it. So when I slice a golf ball as a right-handed player, which way is that ball spinning? Clockwise or counterclockwise? It's going to be clockwise. It's going to be this way, because it's going to go to the right. All right, lefty would be different, but for this purpose, we're going to do something real hard right. So here comes the air, the stream of air coming this way. I'll do a different color so you can see it better. And here it comes. We said because of the Coanda effect, it's going to hug the ball. It's going to hug the ball. Now, remember we talked about viscosity and how air molecules, or maple syrup molecules, they want to stick together because of the viscosity. They don't want to be separated. They move slow. So, very close to this golf ball, you know how there's ridges and stuff on that golf ball? There's basically the air going right at the top of that isn't really moving. It's sitting there. It's just sitting there stagnant, okay? But the air above it is moving with it. So that viscosity, they want to grab each other. They want to hold on. They want to hold hands. They want to move together, right? So this air over here is kind of grabbing the air on the surface, and it's pulling it with it. Now, with the rotation of the golf ball, is that going to speed up this air, or is it going to slow it down if it's going to be going with it?
Speed it up.
It's going to speed it up. So velocity here is going to increase. Okay? And opposite here, if it's going against the grain, it's going against it right here, it's going to slow us down, right? Because the air is traveling this way, golf ball spinning that way, it's going to slow us down. Velocity is going to decrease. Okay? That makes sense? So that's part one of the Magnus effect. We're going to get into part two of why that ball continues to hook right and I have to go find my ball in the other fairway all the time. Because we're going to talk about Bernoulli's principle. Bernoulli's principle states that as a liquid velocity increases, the pressure is going to decrease. We're going to draw something called a Venturi tube. All right, so here's Venturi tube. All right, and I'm going to write a simple equation. This is something you want to remember. So V1 P1 equals V2 P2. Have you ever studied kinetic and potential energy? Kinetic and potential energy are always going to equal each other. You know that? So I take my pen up here, it's going to have potential energy, but as I'm dropping it, that potential energy is changing for kinetic energy, but they're always going to have to equal each other to have a total energy. It's always going to equal. You can't lose energy. Same concept here, velocity and pressure. Velocity is going to be my kinetic energy. Pressure is going to be my potential energy, okay? So we have, let's say, water going through a tube this way. When the water gets condensed, the volume it can travel through gets condensed, what happens to the velocity?
Speeds up.
It speeds up. So if my velocity is going to speed up here, we just talked about conservation of energy, what's going to happen to pressure? What's going to happen to that potential energy?
It's got to go down.
It's got to go down. So pressure is going to decrease. So this equation, velocity 1, P1, is actually in terms to this area right here. This velocity 2, pressure 2, is actually in terms to here. They're always going to be equal. Things are going to change the numbers. All right? So velocity 1, pressure 1, let's say it's 10, okay? Let's say the total 10. We'll have velocity is, let's say velocity is 1 and pressure's 9, okay? So we're changing it. Actually, I don't like that. I don't like that at all. So let's say this total is 10 here. The total is 10, okay? So let's say velocity and pressure 1 are both equal to 5 here. So velocity is going to increase like we said, so let's just go to 7. Pressure then has to, if we want to equal 10, it's got to be 3. Basic math can explain that very simply, okay? So that's Bernoulli's principle. As the velocity of the liquid increases, the pressure is going to decrease. So, back down to the Magnus effect. Velocity increases, pressure is going to
Decrease.
decrease. So pressure decreases. Velocity decreases, pressure.
Increases.
What was that one thing I wanted you to remember about pressures?
High to low.
High to low. So, if I have a high pressure here and a low pressure here, what's going to happen?
It's going to go up.
Hey, that's why I keep finding my ball in the other fairway. Pressure's pulling that ball over. Same thing with the wing. All right, let's draw an airfoil. See if I can draw it good. I'm gonna draw that guy. Mr. Stanchek would be upset. That's better. Let's get rid of this Coanda effect. You understand the Coanda effect before I erase it? Okay. Cool. So, I'll jump over here real quick. So here we have our stream of air coming in this way. Okay? I'm going to go to black so you can see it better. The air, because of the Coanda effect, is going to stick to it. It's going to stick to it. So, so we're going to say the velocity of this up here increases. So the pressure is going to, the velocity increases, pressure decreases. So low pressure up here. And we're going to have a higher pressure down here. Why do you think the pressure up here initially is going to be low? What caused the speed of the increase of the air? So we're going to draw another airfoil real quick. So, when the wind is impacting right here, you get what we call like a stagnation point. It's a pocket of high pressure air from when the wind is hitting it, okay? Now, it's going to hit it, and it's going to shoot this air up here. It's going to shoot this air up here. You ever been in a car before? Take a sharp right-hand turn, If I'm sitting here, I'm going straight and level. Both legs are basically have equal weight, right? I do a sharp right turn, my weight shifts to my left leg. Same concept here. As this inertia of the air traveling over the top of the wing pushes it up, it's going to create lower pressure right here. So here we have a higher pressure pocket of air, stagnation point, and a lower pressure. High to low, it's going to cause that initial increase of air to increase the velocity of the air, which is going to keep making it lower, which is going to keep increasing the velocity of the air going over that, okay? Does that make sense? So that's what's going to give us our low pressure and our high pressure. Now what happens with high and low? High goes to low, we get what we call lift. This is the basic principles and the generation of lift, okay? Now, Newton's law, the one that says for every action there's an equal and opposite reaction, we get something called downwash, okay? So as the air is coming over the top of it, it shoots down here. It kind of goes like this, downwash, it goes like this. So if it's going hard that way, doesn't that mean an equal and opposite reaction would be for this to push that way? Generation of lift as well. So this right here, this little section right here, is how our airplanes fly, all right? It's not magic like Mr. Rogers always used to tell us. It's actually science behind it, okay? Do you have any questions about that? Very good. Okay. So we've talked about Bernoulli's principle, we've talked about Magnus effects, we talked about high and low velocity and pressures and everything like that. We've talked about airfoil design. Now we're going to go over to our last topic is wingtip vortexes, okay? You okay if I erase this? Okay. All right. Let's get a clean whiteboard. All right, wingtip vortexes. Let's say, so airplane's over here, and the wings, I'm looking down the wing like this. So here's the wing of the airplane. So the front of the airplane's over here, the tail's over here. I'm looking this way at the aircraft. Long, so the wings are like the long way here. So as we said, there's a low pressure up here and a high pressure here. Okay? The high pressure area on the bottom of the airfoil pushes around the tip of the airfoil. It wants to get over there. It goes and it comes down and it causes a spiraling effect down. This is what we call a wingtip vortex. Have you ever seen on a 737, or as my dad calls the guppy, those big winglets they have? Those are there simply to prevent this from creating more drag on the airplane. Because the wind vector bends the relative wind vector in a way that brings it closer to drag, these things have a negative effect on air. When we get down into aerodynamics, we're actually going to break it down, and I'm going to show you exactly why these have such a negative effect on it. But for now, you just need to know that the high and low pressure causes this, that when they want to equalize, when they want to come together, it causes this vortex and this spiraling, circulating effect of air out past the trailing edges of the wing, and it has a negative impact on lift. Okay? So that's pretty much the basic principles of flight. That's everything I wanted you to get over, okay? So I'm going to ask you some basic questions just to make sure that you understand what we talk about and the important stuff. So why do we study pressure altitude?
Because we need to know the pressure at.
Right. Remember the pyramid. Pressure altitude leads to density altitude and pressure altitude make me understand performance. It's all about seeing ahead of the aircraft and being in front of it. Okay? So why is density altitude important?
It affects performance.
Performance, exactly. Like we said, it affects the engine, thrust capabilities, and the lift capabilities. Okay? If we have less molecules of air going over the wing, we're not going to have as much lift. Less equals less. Understand that. So what causes lift?
A few things.
Yeah. Few things. Magnus effect, Bernoulli's principle, and Newton's laws of motion. All those in together in accordance with each other create something we call lift. And the pressure differences from high to low. That force, that push from the high to the low is going to cause that generation of lift. And like we just talked about, what causes a wingtip vortex?
The pressure flowing high to low.
High to low is going to cause that spiraling effect down, generating with something we call a wingtip vortex. Okay. So in conclusion, I want to encourage you to go back through the PHAC Chapter 4, and I want you to read up on all this stuff. Bring me questions next time. I want to understand your level of understanding so we can keep working on this. Because like I said, this is a foundation of your aviation career. So if you don't understand this, we need to work on it. Also, I expect you to start reading through some of the next chapter, PHAC Chapter 5, about aerodynamics. As in aviation, you're consistent. You're always studying. You have to be studying all the time. So my dad always said, the day you stop learning, the day you stop striving to learn, is the day you stop being a professional. I know people think of as a professional as someone who's just getting paid, but that's not really the case. Being a professional is a mindset. It's not Oh, I'm getting paid for this job, now I'm a professional now. Cool. No, it's a mindset of understanding and studying and continue making yourself a better person and a better individual in that career field. That starts today. That starts now. So going home and doing your homework makes you a professional. Okay, that's what keeps you professional. So like I said, go through this chapter, review some of the stuff, and then also start getting ready for chapter 5, okay? All right.